Thanks so much, Patrick, and thanks to the entire group for the invitation to attend. I'd like to introduce my wife, Elwo, in the back for those who haven't met her. So we've been having a nice time in Copenhagen. So I'll be speaking today about bounding Gromov-Hausdorff distances with Borsuk-Ulam theorems and Vietoris-Rips complexes. I'll introduce Gromov-Hausdorff distances. They're something I just started researching recently. I assume that some folks in here know about Borsuk-Ulam theorems, and that's how I'm trying to attract your interest. It's a new application of Borsuk-Ulam theorems. Vietoris-Rips complexes, I'll tie in once I get to that board. This is really what I've been studying hard for the last 5 years, so this is my area of expertise. This is joint work with folks from Colorado State, Ohio State, Carnegie Mellon University, and Berlin. We're probably going to make it into some sort of confusing polymath style project with lots of people. I'd also like to advertise AATRM, the Applied Algebraic Topology and Research Network. When the pandemic hit, we already had an online seminar going, so now we've been doing a bunch of YouTube experiments. And we have close to 400 talks on YouTube now, over 3,000 subscribers, and about 24 hours watched a day on YouTube. So it's really interesting to see the growth. I mean, and all of this is new since the pandemic started. So if you're interested in YouTube type things or online math. The broad story is the following. Gromov-Hausdorff distances depend on discontinuous maps between spaces. And as a topologist, what are you going to do with a discontinuous map? Okay. Vietoris-Rips complexes enter because they're a way to turn discontinuous maps into continuous maps. And then once you have continuous maps, of course, you can use Borsuk. So that's the broad picture of how things relate. All right, let me define Gromov-Hausdorff distances. Pretend we have two metric spaces, X and Y. So X is this curve, and Y is the finite set of points, the noisily sampled. So the Gromov-Hausdorff distance is a notion of distance between metric spaces. You say, how close are these two metric spaces? Maybe I'll have my metric spaces be compact. And I'll write down a formula for the Gromov-Hausdorff distance. There's several different definitions. The most common definition is not the definition we'll use in this talk. So let me describe the most common definition out loud. So first you have just the Hausdorff distance between metric spaces. And this is for metric spaces that are aligned in the same space. So here X and Y are both aligned in the plane. Okay. Once X and Y are aligned in the same place, the Hausdorff distance between X and Y is the infimum epsilon, such that if I thicken Y by epsilon, I contain X. And if I thicken X by epsilon, I contain Y. Okay. So I would look at thickenings of the curve. How much do I have to thicken the curve everywhere so that it contains all these points? And similarly, I thicken the points, the balls. And how much do I have to thicken the points in the balls so that the balls contain the curve? So the smallest such epsilon, such that the epsilon thickenings contain each other, that's the Hausdorff distance. Gromov-Hausdorff distance, X and Y no longer need to be aligned in this common plane or any of those. Instead, you take the infimum over all metric spaces Z that admit isometric embeddings from X and Y into Z, and then look at the Hausdorff distance after X and Y have already been embedded in Z. Okay. So it sounds really hard to compute, and it is. It's maybe not quite as hard as it sounds, but it's still quite difficult. Questions so far? I'm going to write down a different definition, which is what we'll use for the talk. And I'll write down a definition for twice the Gromov-Hausdorff distance. It's the maximum of over all maps F, I'll use little g from X to Y, and little h from Y back to X of 3 terms distortion of this map F, sorry, G, the distortion of this map H, and something called the code distortion. All right. So let me draw a picture. Here's X, it happens to be a sphere. Here's Y, it happens to be a circle. And I want to find the best maps G and H mapping between them. G and H don't need to be continuous. They could be, but they don't need to. Yeah. What is the distortion of a map G? This is the main thing that we'll be bounding this talk. Supremum over all input points, x and x prime and x. Okay, so I look over all pairs of points in x and x prime, and I'm going to find the worst possible pair of the sort of difference between the distance in x and the distance in y. So these points I can map over into y, and I get g of x. And I measure how much have I distorted the distances. Okay. So how much have I changed the distances? This is the absolute value, measuring how much have I changed the distances. The worst two inputs that change distances between distances in x and distances in y, the worst two inputs, they give you the distortion. That's also, the definition of the distortion of H going back. We're going to put bounds on the Gromov-Hausdorff distance just by bounding the distortion. We won't use the code distortion anymore in this talk, but let me tell you what the code distortion is. Code distortion between G and H is the supremum now over all x in space x and y in space y. Again, you measure how much of the distorted distances between one space and another. But I'm looking at an input x in space x and an input y in space y. So I can measure their distances in x if I look at the distance between x and h of y. I can say how far apart is their distance in y. Well, I can measure their distance in y by using g of x. So this is the distance in x. And this is the distance in y. And how much do you distort from this? I've got a little tangent to do. Okay, questions?
Small one.
Yeah.
So in your example with the two sphere and the circle, distortion of H is 0. Is that correct?
No.
Because you
yeah, if you do the inclusion map.
If you do the inclusion map, right?
That's right.
And so that means that the Gromov-Hausdorff distance between x and y would be 0 because the infimum.
Sorry, this is the you saved me. This is an infimum over all maps of maximum.
Oh.
Of those three terms.
Okay.
Yeah. So Patrick's exactly right. So the circle includes isometrically into the two sphere. So you can get a map H with distortion 0. But you can't get a map G with distortion. Yeah. And we're going to bound the Gromov-Hausdorff distance between spheres by bounding the distortion of maps from higher dimensions.
So in this case, it's kind of the G which will give us.
That's right. Okay. That's right. Thank you. You saved me. Other questions?
So for anybody online, you can either just unmute and I will hear the questions, or you can also write questions in chat and I will see them and I can ask Henry.
All right, so the following I'm going to describe is from a very recent paper by Mémoli and Smith coming out of Ohio State University. And they connect Gromov-Hausdorff distances to Borsuk-Ulam theorems. Okay. It's just on archive recently. How we got involved is we realized that generalized Borsuk-Ulam theorems could do even more than the Borsuk-Ulam theorems. Okay. So very little is known about Gromov-Hausdorff distances between spaces, and we're going to look at Gromov-Hausdorff distances between spheres of different dimensions. So if I have a circle and a 2-sphere, or the circle and a 3-sphere, what's the Gromov-Hausdorff distance between them? Very little is known. Let me tell you what metric I put in the spheres. So the sphere Sn, we're going to have a geodesic metric. The distance between 2 points is the length of the path. And they're going to have diameter pi. The distance between two antipodal points is going to be pi. Here's what's known. So we get this distance matrix, right? You put all your spheres at different dimensions, and you get this distance matrix. What's the Gromov-Hausdorff distance between any 2 spheres? It's symmetric. So I don't need to put the entries below the diagonal. I can just put the entries below the diagonal. Here are the entries that are known exactly. We have a 2 pi. Oh. The distance between the 0 sphere and any other sphere is pi. So twice the Gromov-Hausdorff distance is pi. Think of this as follows. When you map a higher dimensional sphere down to the 0 sphere, you need to distort distances. Okay, there's this covering theorem that says when you cover a sphere with 2 sets, right? One set has antipodal points. Okay? So the way we're going to cover a high dimensional sphere is we're mapping down to the 0 sphere, which is 2 points. So our 2 sets are going to be the sets that map to the 2 points. Okay? So one of those sets covering the sphere contains antipodal points. So I have antipodal points in the high dimensional sphere that get mapped to the same spot in the low dimensional. And that's distortion pi. If the antipodal points of distance pi in the high dimensional sphere and distance 0. So all of these entries are pi. And pi is the largest entry that you can get in this state. And all the other entries are going to be less than pi. The known values are here we have a 2 pi over 3. So the Gromov-Hausdorff distance between the circle and the 2 sphere is known exactly. And it comes from what Patrick was saying. When you map the 2 sphere down to the circle, you have a certain distortion, and you always have at least 2 pi over 3. And then you can find maps showing that the Gromov-Hausdorff distance. Interestingly, the distance between the circle and the 3 sphere is the same. And this was sort of a clue for me how Vietoris-Rips complexes might be related, as I'll. The distance between the 2 sphere and the 3 sphere is also known. It's R2. What is R2? I'm in the 2 sphere. I inscribe a regular tetrahedron. And this edge length of that tetrahedron is R2. Okay. So 2 pi over 3, I mean, that was actually R1, right? If I'm in a circle, and I inscribe a regular triangle, then this distance here is R1, this edge length.
So the geodesic edge length.
Yeah, and the geodesic edge length is 2 pi over 3, right? Going all the way around is 2 pi. Going 1/3 of the way around is 2 pi. Everything else is only known as a bound. So these entries are all at least as large as Rn. Where what is Rn? Okay. You take the n sphere, you inscribe an n+1 simplex, and you ask what's its length. Questions so far? Briefly, let me just talk about a covering bound. So one way you can bound Gromov-Hausdorff distance between spaces is you can sort of look at packings or coverings of the spaces. And can you pack or cover the space with balls of a certain size? And you sort of have to match up volumes reasonably well when you're getting low Gromov-Hausdorff. So those types of arguments give you bounds here that are not tight. Okay, so they're never going to be tight, really. And so the authors, Mémoli and Smith, they prove the following. For n less than k, twice the Gromov-Hausdorff distance between n sphere and the k sphere is at least as large as pi minus twice this covering number of the n sphere by k plus 1 balls. So let me define the covering number of a metric space. The kth covering number of a metric space X is this is the infimum R, such that k R balls of radius R. So what we're doing here is we're in the n sphere. We have k plus 1 balls. I'm only drawing a couple balls, but you wanna sort of situate the balls as best you can and find the smallest radius such that k plus 1 balls cover it. So the better you can do it covering the sphere, the smaller you make this covering number, so the better you'll have to get. Okay. So we got interested in trying to generalize these lower bounds, and we have lower bounds that you might conjecture are tight, but give lower bounds in particular for this row and maybe for the rest of the table. So here's the theorem that I'll try to spend the rest of the talk explaining. Twice the Gromov-Hausdorff distance between the n sphere and the k sphere is bounded below by the following. Look at the infimum value R such that R satisfies the following. Index, which I'll define, of this Rips complex of the n sphere thickened by scale R, which I'll also define, is at least k. This number, sometimes I might call CNK. So I'll define co-index and I'll define the Rips complex for you. But roughly speaking, what you're doing is the following. You're taking an n sphere and you're thickening it, okay? And you're asking, how much do I need to thicken the n sphere so that it obtains the topology of the k sphere in some sense, okay? So the co-index is sort of saying that when the co-index is at least k, it's saying that you admit an odd map from the k sphere. So how much do you need to thicken the n sphere so that you admit an odd map from the k sphere? Once the n sphere has been thickened enough so that it emits an odd map from the k sphere, then that thickening amount is sort of telling you the Gromov-Hausdorff distance between those two. So this is what I'm going to focus on, this bound. And you might conjecture that this bound is tight in a lot of cases. But just to show you the value of this, in prior work, we had already looked at this number and we had shown that it was bounded by the covering number in projective space. So now when you're trying to cover projective space, it's sort of like you only need to cover half of the n sphere. So you expect to be able to cover the projective space with smaller balls, right? So we're going to have a smaller covering number here that we subtract. So we're going to have a bigger lower bound than when you look at this covering number. So this is sort of just an argument that comes out quickly. And I won't really talk about coverings anymore. One thing that we know already about these values, C and Ks, is we know of these values. So we know that this is at least 4 pi over 5. This is at least 4 pi over 5. And then this is at least 6 pi over 7. And this one is at least 6 pi over 7. So why are these entries coming in pairs? Well, you'll see that in a moment. But that was our clue to try to relate Rips complexes in the first place. We saw this pair of numbers. We said, that has something to do with Rips complexes. And now we're able to prove balance here as well. Okay. So I owe you some definitions. I need to define the co-index. I need to define the Rips complexes. Other than that, questions right now? I'll talk about Borsuk-Ulam. This is where the co-index is entering. What is a Z-mod-2Z space? It just has a free involution. We'll write this as X maps to negative X. So spheres are all Z2 space. You can map a point to its antipode. What is an odd map? It's just a Z2 equivariant map. So an odd map between two Z2 spaces satisfies f of the antipode of an input is the antipode of x. F of negative x is equal to negative f of x. What's the co-index of a Z2 space Y? It's the largest K such that there exists an odd continuous map from the K sphere. So it's hard to admit maps, odd maps from K spheres, and the co-index is the largest K sphere from which you admit an odd map. So what does the Borsuk-Ulam theorem say? Says something about the co-index. Borsuk-Ulam says that there's no odd maps from a higher dimensional sphere into a lower dimensional one. Okay. So the largest K sphere that you can map into the N sphere is at most N. Okay. So the co-index of the N sphere is at most N. That's sort of what Borsuk-Ulam says. You can get an odd map from the N sphere to the N sphere, but you can't get an odd map from a larger dimensional sphere into the N sphere. And then, of course, you can have an odd map from the N sphere to the N sphere, just the identity map. And that's shown that this is inequality. So when we're thickening these N spheres using Rips complexes, which I'll define in a moment, when we're thickening them, and we're thickening them in order to sort of obtain the topology of the K sphere, that's precisely what I mean. You need to thicken the N sphere such that you admit an odd map in. Happy? All right. And now I'll define Vietoris-Rips complexes. X is a metric space. You have a scale parameter R that's positive. So Vietoris-Rips complex, which is denoted BR of X. It's a simplicial complex built on top of this metric space. So Vietoris was a topologist. He wanted to define cohomology for metric spaces. So he built simplicial complexes on top of metric spaces to define cohomology theories there. Rips is a geometric group theorist. So he wanted to thicken groups in order to study their finiteness properties. Okay, so the Vietoris-Rips complex has X and sigma, finite subset sigma complex. If the diameter subset R, the diameter of a simplex is just the length of its longest edge. So here might be my space X, and choose a scale that's a couple inches. What's the Rips complex? Well, whenever 2 points are within that distance, I have an edge between them. And then whenever I have all of the edges of a simplex, then I glue in that simplex. So I glue in this triangle here. I glue in this second region here. And the reason why I've studied Vietoris-Rips complexes is because I'm coming from applied topology, studying the shape of data. And this is one of our most common tools for approximating the shape of the data set. Right? You have a set of points, a data set. It has no topology, but if you thicken it a little bit, then you get. We're going to be thickening n spheres. So we're going to have these simplicial complexes with an infinite number of vertices, right? One vertex for every point in the n sphere. And we're going to have simplices of arbitrarily high dimension. Okay. An important property is that Rips complexes sort of turn discontinuous maps into continuous ones. So a map between two spaces that may be discontinuous, it induces a continuous map between the Rips complexes. We're going to map a vertex to f of x. And then once I know how to map vertices, I know how to map simplices. Right? I just extend linearly simplices. I need to check that it's well defined though, right? I need to check that if I have a simplex in the domain, that it maps to a simplex in the codomain, not something that's not fitting into simplex. So pretend that I have a simplex in this Rips complex. Every distance between vertices here is at most r, right? When I map forwards, how much can I increase the distances, right? The distortion tells me how much I can increase the distance. Distances increase by most of the distortion of the map. So as long as I give myself a scale parameter that's larger, r plus the distortion of f, then, well, if all the points here were distance at most r, here all the points are distance at most distortion of f plus r. And it's continuous. I mean, f could have been discontinuous, but when you map between simplicial complexes, yeah, it's a well-defined continuous map. So that's going to enter when we turn some of these discontinuous maps, possibly discontinuous maps, in the definition of Borsuk, in the definition of Gromov-Hausdorff distance. That's how we're going to turn them into continuous maps. So we can use topologies. Questions? Okay.
Henry, a question about the table.
Yep.
So in each row, it converges to pi, the distance, and you gave bounds on the entries, but can you say something about the rate of convergence? That maybe if you go down the rows, the convergence is slower?
Great question. So I'll repeat it out loud. So the audience member is conjecturing that in each row, the Gromov-Hausdorff distance is going to converge to pi. Right? So pi is sort of the maximum entry in the table. And, you know, as you fix the dimension of the n sphere and you look at higher and higher dimensional k spheres, right, that distance should go to pi. That's almost certainly true, but it hasn't been proven. Okay, so everyone would conjecture that, but it's not proven. These authors did define a metric on the infinity sphere, and they looked at the distances between any sphere and the infinity sphere, and it is always pi, right? But, well, maybe these covering results imply that it goes to pi. Ah, you're right. I think these results imply that it converges to pi.
Right, but I asked about rate of convergence.
Yeah. Okay, right. So these covering results imply that as you go along the row, it converges to pi. I mean, these bounds give you some rate, right? But I don't know too much about it. Of course, a ton of work has been done on coverings of spheres. I'm not an expert. I'm sure a lot of work has been done on coverings of projective spaces, but I cannot find much. Rate of convergence, I can't say anything off the top of my head. You could get bounds on the rate of convergence using these bounds, but we don't know if these bounds are tight. So maybe it converges actually faster than what these bounds would give.
Okay, thanks.
It's not even proven that as you move to the right in a row, the distances get weakly bigger. Okay? So to our knowledge, a distance as you move to the right in a row could get smaller. So I was shocked by this, but I asked Mémoli, who's one of the experts, and he's like, yeah, as far as we know. Other questions? So next I'm going to go into some work I've done on Vietoris-Rips complexes, which is how we were able to recognize this pattern that they should be related from these two numbers. All right. So with Michael Adamaszek, who actually was a postdoc here in Copenhagen, and we had dinner with him last night. We proved the following facts about the Rips complexes of the circle. So you have some circle, and you're building a Rips complex on it. So you might have 100 points that are within distance R from each other. Okay? So you have a 99-dimensional simplex, even if R is quite small. But for small scales, what you get is sort of some like infinite dimensional solid torus. This is of arbitrarily high dimension, but you can contract everything back down to the circle. So for small scales R, here R is increasing from left to right. You maintain the homotopy type of the circle until you get to 2 pi over 3. At 2 pi over 3, what changes is you have this equilateral triangle. Okay. Triangle gets glued in. You might think everything becomes contractible then, but it doesn't. You get the 3 sphere. And the reason why you get the 3 sphere is I had this, coming from the circle, I had this infinite dimensional solid torus sitting in front of me. Right? I'm thinking of this in 3D space. And then I glue on not one disk, but a circle's worth of disks. So I fill out all of 3D space plus a point at infinity. I decompose the 3 spheres, 2 solid tori glued together. One solid torus was just coming from the circle and the simplicity of the circle. The other solid torus is coming from this circle of equilateral triangles. Yeah? So that's how we knew the connection, right? At scale 2 pi over 3, the homotopy type changes, and the homotopy connectivity jumps by 2. Right? That's sort of why you have 2 entries that are equal. Right? So what happens next is at scale 4 pi over 5. This 4-dimensional ball fills in. And if 2 or 3 sphere, you glue on a circle's worth of 4-dimensional balls, you get the 5 sphere. Okay, and then this continues, you get the 7 sphere, the 9 sphere for smaller and smaller scales, until eventually you reach pi. It's factorable. So this tells us what some of our C and K values are. The smallest are such that the co-index of the Rips complex of the n-sphere is at least K. So C1 2K plus 1 is equal to C1 2K, which is 2 pi K. 2K plus 1. Because how much do I need to thicken the circle until I admit a map from the 2 sphere or the 3 sphere? Right? When I've only thickened the circle this much, it's homotopy equivalent to the circle. So by Borsuk-Ulam, there's no odd map from the 2 sphere or the 3 sphere. But once I thicken my circle by 2 pi over 3, I get the 3 sphere. And then the 3 sphere does emit an odd map from the 2 sphere and the 3 sphere. That's why the co-index is 2 pi. And then how much do I need to thicken the circle until I admit an odd map from the 5 sphere? Well, I need to thicken it to 4 pi over 5. So these C and Ks are just all these entries, which is here. Questions so far? Next, I'm going to tell you the little that's known about Rips complexes of n-spheres, and they recover these lower bounds. Right here, right with the diagonal. So now take an n-sphere and thicken it by some scale. What's the homotopy type? For small enough scales, you still get the n-sphere. And then at scale Rn, right, which is the diameter of this inscribed regular n+1 simplex. The homotopy type changes. You actually get Sn join S1 + 1 by n + 2. Let's look at the case of the 2 sphere. N is 2. I thicken the 2 sphere, I get the 2 sphere for a while, and then I glue in this regular tetrahedron, and the 2 sphere sort of fills in. How does the homotopy type change? Well, it's the homotopy type I had before, the 2 sphere, joined with the parameter space of tetrahedrons that I glued in. And SO3 tells me all of the rotations of this tetrahedron I can have in 3 sphere. E4 is the symmetries of the tetrahedron, rotational symmetries. So this is sort of like the parameter space of tetrahedron I glued in, joined with the space I had before. That's really where this 3 sphere was coming from. This was the circle, join the circle. The circle I started with, joined with the circle's worth of equilateral triangles. This jumps the co-index by 2. Okay, so the co-index Cn n + 2 is equal to the co-index Cn n + 1. So I know these values of C and Ks here and here. So I mean, I definitely also have at least R2, at least R3, at least R4, at least R5. Probably these are all equalities, but no one's proven that. here, the maximum case such that a map in the case is n, but then this space emits a map from the n+1 sphere and from the n+2 sphere. So that's why we would conjecture that these lower bounds are tight and they're the same on both of these super diagonals. Okay, questions? Nothing's known about what's later, except I've been thinking hard for some time about what are these later homotopy types, right? And no one really knows. Maybe afterwards I could say a little bit more is known in the case of the two sphere about what might happen. But the nice thing is that we've linked these two problems now, right? If you could say things there, you can say things about these homotopy types and vice versa. You can say things about these homotopy types as thickenings of spheres. So, okay, I think I've been going for about 45 minutes. I don't have that much more, so I won't rush, but I'll try to get through it in, say, 10 minutes. I want to describe a version of the Borsuk-Ulam theorem that I suspect few people have heard about. I want to generalize it, prove that generalization of the Borsuk-Ulam theorem, and then with that generalized Borsuk-Ulam theorem, we'll be able to prove this theorem bounding the Gromov-Hausdorff distances. Okay? So I think this generalization of the Borsuk-Ulam theorem is interesting in its own right. Here we use it for Gromov-Hausdorff distances. Maybe you'll find other uses. There's no continuous odd map from the n+1 sphere to the n sphere, right? That's what Borsuk-Ulam says. No continuous odd map. Dubridge and Schwartz tell us how discontinuous must this map be. They bound something called the modulus of discontinuity, which is saying 2 points here that are arbitrarily close must go at least yay far apart. We only need a weaker result, so that's all I'm going to write down. Odd maps from an n+1 sphere to an n sphere, well, they can't be continuous, and we can say something about their distortion. The distortion is at least Rn. The diameter is described n+1 species. Okay. So that's how the Ohio State crew proved those lower bounds on the superlight. Our generalization is just, what if I go from the K sphere, the N sphere, and K is bigger than N. We prove that the distortion is at least these values C and K. Okay. So these C and Ks were how much did you have to thicken the N sphere until you admitted an odd map from the K sphere. All right. The proof of this generalization. Fix an epsilon bigger than 0. We're going to pick a finite sampling of the K sphere that's pretty dense. It's an epsilon over 2 net. So every point in the K sphere is within at least epsilon over 2. At some point in our finite sampling. And we want it to be antipodal. So when you reflect the set, you get the same thing back. Now we're going to produce an odd continuous map from the K sphere into a Rips complex of the N sphere. All right. So here's our case here. And then over here, what we have is we have this sampling X. And on top of X, we build a Rips complex. So we glue in all these triangles. The balls of radius epsilon over 2 around X cover the K-sphere. That's what it means to be this connect. Okay. So the way you produce this map is just a partition of union. Supported on all these balls, you have these bump functions that sum up to 1. Okay. So when I want to map a point on this K-sphere into this Rips complex, I say, what are the bump functions that have positive value? Those are my barycentric coordinates when I map this. So a point in the K-sphere that's like in the intersection of these 3 balls. If the bump functions are positive values, you're going to map into the interior vectors. This map is just the map over here, right? I was given a map F from the K-sphere to the N-sphere. So certainly I have a map X. I have a map F from X into the N-sphere. So I have a map from the Rips complex in X into the Rips complex in the N-sphere, where I just need to thicken the scale by the distortion of that map. So this is again just a point maps to F of that point. So I built an odd continuous map from the K-sphere into the Rips complex. From a discontinuous map, this value must be at least CNK. Because I built an odd continuous map from the K-sphere in here. C and K was the smallest scale such that this Rips complex emitted an odd continuous map from the K-sphere. And this is for all epsilon. So the dispersion of F is at least C and K. So sort of as Patrick said at the very beginning, I'm bound in these Gromov-Hausdorff distances. I'm going to bound Gromov-Hausdorff distances using bounds on the distortion from the high dimensional sphere to the low dimensions. And now we can prove this theorem. It's done right here. Twice the Gromov-Hausdorff distance. Well, it's at least as large as the infimum overall maps from the high dimensional sphere to the low dimensional one of, the Gromov-Hausdorff distance is the maximum of these 3 terms. So it's least as large as one of them. Okay. Next, we're going to do this trick. We want to apply this generalization, but this generalization is for odd maps. Right? We don't need this map to be odd yet. But it turns out you can get away with it being odd. And this is by a trick from the Ohio State authors. Okay? So given any map between spheres, you can produce an odd map between spheres that doesn't increase the distortion. And all you do is take the map between the spheres and restrict it to the northern hemisphere. And then whatever it does on the northern hemisphere reflects that. And amazingly, you just do a computation that doesn't change it doesn't increase the distortion. And now by a generalization, this is at least CMK. Generalization, oh, I should say odd here. That was the whole point. I said that given an arbitrary map between spheres, you can find an odd one that doesn't increase the distortion just by taking the map on the northern hemisphere and reflecting it. And then we apply our generalization of Borsuk-Ulam. That's always C and K. That's giving those bounds. So some open problems to end with. These are lower bounds, but you'd like to prove that many of them are equalities. And the way you typically do that is you find surjective maps from the high dimensional sphere onto the low dimensional sphere that sort of obtain those values. These are going to be discontinuous maps. What if you had spaces, metric spaces that were G equivariant, right? So you wanted to bound Gromov-Hausdorff distances between families of G equivariant spaces. Can you use any of this machinery there? Florian Frick, who's my collaborator, he wants to think about versions of this for Tverberg type theorem. So when you prove the Tverberg theorem, you know that continuous maps from a high dimensional simplex into low dimensional space identify things, right? You have some, you don't use the Borsuk-Ulam theorem, but you use a G equivariant version of the Borsuk-Ulam theorem. That proves that no continuous map exists. Well, with that theorem, if you had such a map, how discontinuous must it be? And I'll end there. So thanks for your time and attention.
Thank you very much. Are there questions either from here or also from the online participants?
Yeah. That's right. It's like,
I'm not sure whether people heard that online, so if you could maybe repeat the question. Yeah.
the question was, how did I get this bound in this step in the proof? Is that right? That's right. That's right. So the Gromov-Hausdorff distance, you infimize over all maps, but once you've sort of fixed maps G and H, the Gromov-Hausdorff distance is the maximum of these two distortions in the code. We're trying to bound this from below. So we're trying to show this Gromov-Hausdorff distance has to be at least sufficiently large. So you can't just bound one of them. And the one that so far people have been able to get the best bounds on is the one that maps from the high dimensional sphere to the low dimensional. But you're totally right. I mean, maybe you could try to get better balance by involving. We ignored this co-distortion in the entire talk. Yeah. So I am an optimist, and I would like to hope that these C and Ks, which are related to Rips complexes, are exactly the Gromov-Hausdorff distance, right? So I would hope that these are equalities, but I might be totally wrong, and maybe by using the co-distortion, you can get smarter and better lower bounds.
All right, other questions? So I have one. This last thing that you mentioned, that Florian Frick is interested.
Yeah.
So yeah, these distortions on these Weber type maps, would that have any combinatorial interpretation?
I think that's the hope. So you know this better than me, I'm sure. Or somebody here probably knows what is the equivariant obstruction that's used when proving. I mean, it's something for like probably Z mod P.
Yeah. So I mean.
Okay, so it's a Z mod P equivariant obstruction. So there's no Z mod P equivariant map between these two spaces. Right? And yeah, I think that's really the hope is now maybe not just combinatorial, but some meld between combinatorial and metric. Right? Because now what you'd want to do is you want to say, given a Z mod P map between these two spaces, if it is Z mod P equivariant, it has to be at least yay discontinuous. And now you're sort of like blending the combinatorics of Theorem with the metric of how quantitatively discontinuous are they.
So there's some kind of a quantification of how much these things are.
sizes of simplicities. So, I mean, the reason why we were able to come up with this generalization is, I mean, these are Borsuk-Ulam theorems for maps from high dimensional spheres to low dimensional space. Previously, we had looked at Borsuk-Ulam theorems for maps from low dimensional spheres and high dimensional space, also using Rips complexes. But there you say things like you map from a low dimensional sphere into a high dimensional space. Doesn't need to intersect, right? But you can find simplices of bounded diameter that intersect. So you sort of look at convex holes, etc. So yeah, you're exactly right. You want to try to use that equivariance to say something that the line's coming towards and
Any other questions? That does not seem to be the case. So let's all thank Henry again.
thanks so much.
That's the recording.